So last time we started talking about the forces due to pressure on submerged flat surfaces. And what we did was we found the magnitude of the force due to the water or fluid pressure on that flat surface. Okay, so what we had was some surface and it's submerged underwater or under any fluid. Let's say we have atmospheric pressure acting there. And what we found that the force, the magnitude of the force, is just the pressure at the center of gravity, which is really the centroid, wherever that may be, times the area, okay? Where the pressure at the center of gravity is going to be the atmospheric pressure here at the top, and then it's going to increase as we go down by rho gz. All right, so it's just going to be P atmosphere plus hcg. Well, remember, hcg is a vertical distance in the direction of g from the top down to your center of gravity. Okay, so that gives us the total force on top of the plate. And if we were looking at the bottom of the plate, we would get the exact same thing, only the force would be going up and to the left instead of down and to the right. Remember, the pressure force always acts normal to a surface and towards the surface. Okay, so the next thing we need to find is where this resultant force acts. So we have the magnitude, we need its position. Okay, in order to visualize this a little bit, let's divide that pressure field into parts. Remember, the pressure field was a distributed load. Looks like this. We have the pressure at the top of the plate, and it's going to increase linearly till you get to the bottom of the plate. Okay, so let's divide this into a rectangle and a triangle, where this rectangle is just a constant pressure field, constant distributed load across there, where this is the pressure at the top of the plate going all the way down. Okay, so you get that, and then this part of it is a triangle. That is showing how it's increasing, how the pressure is increasing from P1 up to the total pressure at the bottom. And that's going linearly, and that becomes a triangle. Okay, so if we look at this distributed load just from the rectangular part, well, that's just going to act, that's the same everywhere, so that's going to act at your center of gravity. But if you look at the triangle, you get a higher force due to pressure down here at the bottom, right? So that's going to shift your resultant force down, deeper, okay? And taking these two together, you're going to get a resultant force somewhere in between, but it's always going to be deeper than the center of gravity. And that we're going to call the center of pressure, or CP, center of pressure, always deeper than the center of gravity. Okay, so what we need to do is find where that actually is. And we have some equations down here. What that comes from is just summing the moments. The sum of the moments around CG, you're going to have the moments due to your resultant force that you're getting has to equal the moments due to the whole distributed load, which is going to be an integral y p dA, right? As the pressure changes as you go down. It's not that hard of an integral because it's linear, but that's already been done. You always get the same thing, so we might as well just use the equation that we've got, and that is that are these. So xCp, so let's remember this surface could be anything. I think we had something looked something like this. And the way we draw our axes are y is going to go straight up the surface towards the level of the air, towards the air, I guess you'd say. So here's our center of gravity on this, looking straight on at this surface. Y is going to go this way. X then up here would be coming out of the page at you. Okay, so it turns out though that xCp, so x where that force is going to act, let's say we have a force over here on this side, we're also going to have a force over here on this side. So if this whole surface is symmetrical about that y-axis, which a lot of times it is, a lot of times we have a rectangle or a circle or something symmetrical around there, whatever force we have over here, it's trying to push it so it twists like into the page, is going to be counteracted by this, trying to twist it the other way into the page. All right, so in the end, the XCP is going to end up being 0 if that's the case, if it's symmetrical, and it's going to end up right on the y-axis. YCP, on the other hand, is not going to be 0. That is going to be always a negative number deeper down than the center of gravity. Okay, and what it is minus rho g IXX sine theta over PCGA. So what is that IXX? Well, just like what you had in statics. It's the moment of inertia. And for the common shapes that we'll be using, you're going to find that moment of inertia equations in figure 213. Remember, when you're finding that, just like when you're finding that center of gravity, you want to pretend you're looking normal to the plate. Don't pretend you're looking straight down from the top or from the left or anything like that. You want to look normal to the plate to find those. And then you're just going to basically plug it into those equations. Remember, YCP will always be negative because this center pressure is always below the center of gravity, and our axis is always going up the surface. Again, XCP will be 0 if it's symmetric about the y-axis. And also remember, these pressure forces always act towards the surface. Okay, so again, if we were looking at the bottom of the surface, it would be going in the opposite direction. And it's always normal to the surface. And the area, just like with the shear stress, is always where the pressure acts. So a method to solve these problems, first thing you want to do is find your force, your magnitude of your force, and that's PCGA. So pressure at the center of gravity, use your hydrostatics to get that, times that area where the pressure is acting. Then you want to find the position if you need to. You don't always need to, but a lot of times you do. Find YCP, and if it's not symmetric about the y-axis, then maybe XCP. Maybe you'll need XCP. Usually you don't. Okay, that's not usually the end of the problem. Usually it's not saying, okay, find a resultant force and where it acts. It's trying to find something else. And normally what you're going to need to do at that point is draw a free body diagram on the surface, or solid object, or whatever it is that you're trying to figure out some forces on. And then use your statics equations. Sum of the forces equals 0. Sum of the moments equals 0, as needed to figure out whatever the problem is asking for. All right, so now you have everything you need to know, but there's one little simplification that can come in handy sometimes, and that has to do with atmospheric pressure. So many times when we're doing these problems, let's say we have this problem right up here at the top, we see that we have atmospheric pressure acting on the top of this surface through the fluid, right? So you've got P atmosphere up here. If we were also doing the bottom of the surface, like the bottom of this plate, we would also have P atmosphere working on that, right? So we could say, okay, we have this force due to P atmosphere acting on the top. We have an equal and opposite force due to P atmosphere acting on the bottom. Those two are just going to cancel each other out. They're constant on both sides of the surface. They're going to cancel each other out. And basically, anytime you don't have some sort of enclosed, pressurized, or vacuum tank, that's going to happen. Even if it's going through the ground or whatever, you're going to have P atmosphere somehow acting on both sides of your surface. And when that happens, what you can do is cancel out that P atmosphere in your equations, and you get a little bit simpler equation. So in your magnitude of your force equation, that's PCGA, remember? Before we had P atmosphere plus rho g HCG to get that PCG. Well, now the P atmosphere is 0, right? If we have that P atmosphere acting on both sides, we can just use gauge pressure, and we'll say P atmosphere is 0 because it's not going to have an effect. So we can just get rid of the P atmosphere part, rho g HCG A, and then we can just write that as gamma HCG A. Nice and easy. All right. And the same thing with our XCP and YCP equations. They simplify a little because you're going to end up with a rho g in the top and a rho g in the bottom that can be canceled. Minus IXY sine theta over HCG A. And similarly with YCP, minus IXX sine theta over HCG A is what you get, because the rho g's that you had on the top and bottom will cancel out. Makes it a little bit easier. All right, so go ahead and stop here and do questions 1 through 3 in your quiz, and then we'll go through an example.